那川普感觉对习近平这么友好，受不了。还要他们做这个，可是这不是带给共产党失路？受不了，受不了，受不了。那为什么陈景生和邱振东跟他妈也不看到？不懂。那陈景生文化大革命的时候来中国考察过，他回去那些西方学者说，因为中国近代保持企业所以需要这种强大的集体主义来凝聚联系。啊，我很扯。为什么这种头脑这么顶尖的人的观点会是狭隘的？也不是狭隘吧，就是有那么人被影响，或者说只是被那个无解什么一种概念成一个东金宝怎么讲？也理解是上次是开始讲了一点，
嗯
相对理想一半的时候，
嗯，
然后金马奖就是配一下，
啊，
金马奖就是配一下。
对，呃，
我去快点去让他提个奖，
有
关系在哪？
工具哦，会不会提工具？
就是没有什么 special，
对，
全部没有。
看不到都不会说。
被发从 best play 到有特
好不好？哎，
啊，这样一半的那个从 best play 还有什么特别？
因为那边它其实是那个 point correct，point correct list 那个 model，就是说你可以有一个 SL2 的 action 在上面，然后你看过 point correct list model？
没有，但是我看到你说那个 SL2 啊，
对，
这不就是 A 再加 B 或者 C 再加 B，
就是它有一个 action 哦，这个上面，然后可以算 partition 嘛，好像是 partition，可以 partition 掉整个。
它的 module
我觉得风哦，因为风是在看这个 SL2 的 X 吧，但是它 SL2 的 X 在 OK 方面。因为如果你去玩那个 action 的话，它就天然就是做一个 X 这个东西，因为那个 MC 的东西。
样子讲也好。我没有让他 master 过比我们轻松很多。你问他们，怎么可能轻松？你们只需要上课都不用做 FIP，只需要上4门。啊，
又没有 return，
对，又没有 return，可是有4个 project，我们也有 project，这个算比较好的，之前也有啊，我们 FIP。
我是要下载你先给我的东西，还没有下载。
这样你跟你出门那里会拉稀了，要比如拿那个皮，你是觉得拉稀了？为什么？我觉得你们现在是我们啊，我们想，我们这个意思。我那是已经说了，现在摆了。好像我在说什么？我刚刚一起把另外一个说出来，你们做的用。因为我那些呢，financial management 嗯，同意啊，是不是？我们考的是全部诶，从 Web 1到 Web 14。哦，对，上课不错。对，继续。但是考试就能打。对，我愿有马来西亚人最好是没有升学压力。啊，我怎么淘汰了嘛？我也是这样觉得。你看没定了？小孔。嗯嗯，这里。嗯，对，那就是这样。他们叫 ANT，然后又有 ANC，然后 AE。这个可以成为你的都可以。对啊，我也没给啊，我偷到了，看不出来，悄悄 hack 进去你们的电脑。对，我那天晚上洗车的时候给他50块钱，我这样，他就给我不给他100元。如果是我的话，我不用那个框在最下面要段开了进去。 让我再跑一次。
这个
这样给他弄个什么 not break 什么就等于 for 等于 true，这个死亡定律。
嗯，
应该讲多久？
取决于你要问什么题目。我可以
学我不是忘记了。在床上播出。
要整个吗？
不是在游戏里面，按出是看，就修改它。
我有，有，
今天我一节课。
要整个。
一点，等高。
可以用慢用
啊？
可以用慢用。
正常。相关。哎，你可以把这个你有那边可以重更好，重更好。
Screen
GPU。我个放空的。
哇，这个展开哦。
哦，你摸那个旁边，那个上面一个。
开始连接话筒，已解锁，请取出话筒。
这个那你继续玩吧，谢谢。就好。 已经开始。Okay, so good afternoon, everyone, and we continue. And firstly, I want to say something that I missed in the last lecture. And last lecture, we have a definition say that the primitive stuff f is primitive if for all principal prime ideal, f is not in the PRX. But there is a general case, but in this session, we are focused about UFD if R is UFD. So we have the lemma here. F is primitive if and only if the GCD of the coefficient is equal to 1. So the proof is in the UFD, the GCD is not equal to 1 if and only if there exists an irreducible element Q such that the coefficient is in Q. So we have I think before they have the proposition say that if R is UFD and A be an irreducible element, so A is prime, so here that Q is prime. So, and the next, wait, so we don't. Okay, sorry. And then next, I think I also need to prove the lemma 0.1, 0.10. So, it say that f is equal to const f, the f under bar, where f is primitive, and if f is equal to cg, where c is the ring and g is a primitive, then c is a const f. So this one is actually quite obvious from the definition of the lemma. So actually, I missed the lemma, and we can just treat the const f be a GCD of coefficient. So it is just simple proof by the lemma definition. So actually, we can say that if we have f equal to c g, then c is called f if and only if g is primitive. So this one is just had the because f if I have the GCD or coefficient equal to something A, and then const f is actually the GCD or coefficient. So I take the A out. So automatically my f under bar will have GCD equal to 1. And GCD equal to 1 means that the f under bar is primitive by the definition. So for the part 1, we have said that if a ring is UFD, the polynomial ring is also UFD. We already proved that. So for the second part, the irreducibility of polynomials. So we have talked about the 2.1 rules and reducibility, and we have said something is related to our secondary school, but a little bit advanced. It just say that mostly talk about the case of the polynomial of degree. Okay, so next. Okay, next section 2.2, we need to add rules and talking about the algebraic cost fields. So next proposition will be like that. So let's
那个白的，
出来了，没有，没有，
对不对？来得及。
没有，我觉得那个卡，你看那个卡，OK，好，OK。Sorry, so we continue. So, we let K be a field. So, and let any polynomial be the inside the polynomial ring of the field. So, let the polynomial be a non-zero irreducible polynomial. So, actually, we have the big F. We define the big F as the polynomial ring quotient, the ideal of the FT. So we say that that one is a field with the natural homomorphism K to the BF. So actually that one is obtained by the composition from K to the polynomial ring to the BF. So there is an extension, okay? So furthermore, so we have the 2 points below here. The F has a root in the BF, so namely that one is a coset of T. So if if the big K contain the small k is any extension in which the F has a root, so there is a homomorphism from the BF to the BK such that the diagram commutes. So let's talk about the OK， 哎，随便啦，有没有意思就好了。
没有啊，奇怪，
OK，回去改。
好啊，奇怪啊，没唱开吧？不能翻过。
So the first sentence, since K is a field, the polynomial is a PID. So this one actually in the textbook that left as an exercise. So since Fx, so we have the proposition 0.2. If we assume that I is a PID and I be the non-zero ideal, so the I is prime if and only if it is maximal. So we have that. Since the FT is non-zero irreducible polynomial, so the ideal ring FT is a maximal ideal KT. So therefore, the is prime. So we have therefore F BF is indeed a field. So we have the denoting concept of the KT over the ideal FT. So actually we have here an and then T underbar to our N plus blah 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 plus A1 T underbar plus A0. So it actually equal to A N T N underbar blah 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 A1t underbar plus A0 goes underbar, and then is automatically equal to the ft underbar. So it's equal to 0 since we have the ideal of ft as a quotient. So now we go to verify the second part, the diagram commutes. So suppose the k is in the big K is an extension such that we have an element in the big K such that fu is equal to 0. So this means that we have the homomorphism from the kt to the big K. So we can define there is what epsilon gt by equal to gu. So if we put ft inside is equal to fu is equal to 0. So we say that vanish at ft. So we have the ft, the ideal ft is inside the kernel. So we have the universal property of quotient. So it gives the homomorphism like bf to bk. So actually this one is after we have the unique homomorphism, we are done.
我这边可以看。
那边有个线，
有啊，没有，你没有拉出来，
对对，各种工作也不行。
不是你还没有拉过来这边，
我知道，
你应该可以吧？
对哦，
是没？我嘞，没有，
我不知道你可不可以连。
我现在调了，把连你那边有东西，你的 view 那边不能咩？哦，I don't know，你 full screen 看，然后你 hide me，应该也没有，哎，这个可以吗？没有啊，我这边有什么？诶，我这边没有，不懂诶，我这边 focus 了哦，就这样，够大吧？
直转，停止出入口。
你开没开？
OK，好。
你麦也没有开，诶，我开了，我开了，
那我就不要害我自己，
你要开，不要开也可以，
我不知道。
你那边我 option，那你安排。
OK，千辛万苦啊。OK，we time to verify the second part of the statement. So, uh, yeah, we until okay empty. So okay, yeah, we already done. So the one is we use the universal property of the quotient. Okay, so we come for example. So this one example is I think a very classical example. So actually we just say that the Rx over a quotient x squared plus one. So it's actually isomorphic to Ri and actually isomorphic to the complex number. So next one, we go to the definition algebraically closed. So a field K is algebraically closed if all irreducible polynomial in the polynomial ring have degree 1. So here come to the lemma. So we have, I think this one is TFAE, but I don't know why the textbook write out if only if. So a field K is algebraically closed if and only if.
TFAE is if only
是吗？
啊，对啊，TFAE is if only 是啊，你讲 I don't know why 啊，
Yeah，可是我觉得还是 TFE 会比较 list one to three 的，而且有3个。
but if only 也是一样的，
最有趣。
So the second statement is every polynomial f factored completely as a product of linear factors, and the third statement is every non-constant polynomial has a root in. Okay, so that one I think very obvious from A to B. So assume K is algebraically closed. So and every irreducible polynomial has degree 1. So I let f be any polynomial. So since K is a UFD, so the ring polynomial is a UFD, so f factors into the product of irreducible polynomial. So actually for every polynomial, we can factors into the irreducible polynomial, and we say that irreducible polynomial has degree 1. So we already done, it can factors completely as a product of linear factors, that is the degree 1. Linear factors means degree 1. Okay, so actually from B to C, since it can factors complete as a product of linear factors. Linear factors means that we have x minus a, right? So every non-constant polynomial has a root. The root is actually f. This one is b to c. I just want to quickly go to because this one is simple and obvious. I got the proof that this, but I just quickly go to. So from c to a, if every non-constant polynomial has a root in Kc, so we consider an irreducible polynomial in Kx. Polynomial in Kx. So we let A be the root of F. So actually, we say that F is irreducible and A is the root of F, but we must have x minus A equal to F, because we say that for the hypothesis we have the polynomial has a root, so this one must be device F, and we say that F is irreducible. So we're done. Every irreducible have the degree 1. Irreducible polynomial have degree 1. Okay. So
multiple of x minus a, a unique time x minus a.
x minus A device F. Okay.
I mean, like, can be a unique time x minus a, right?
Yeah.
Huh?
Yeah.
把你这些 x minus a 可以是任何的 unique time x minus a 吧 ？Irreducible definitions of
I think not consider as the constant. The constant no need to factorize out the irreducible one. Irreducible polynomial means
yeah.
Maybe the implicit if cannot refer to the your system.
Irreducible definition.
if I have irreducible polynomial cannot be factorized as the product of
some
polynomial. Right.
对，我叫 polynomial。constant 也是 polynomial。
找吧。
If A is B equals to B, then B is equal to C.
B is what？
If A equals to B, then B is C.
对啊 ，B 是 unique 有 C 是 unique 啊，所以是可以是有 unique 层在上面，不一定是 F 等于 x minus a， 只是一个 unique 层 x minus a。Because 你可以想象 like 2x minus 3也是一个 irreducible， 对吧？
对呀，会在哪里？ So
你的 proof 里面写 F 等于 x minus a 没有哎？对啊，你看 because
so you
yeah，
sorry. Okay. Okay. So next proposition we say that K is algebraically closed field implies K is infinite. So this one we prove by contradiction. So we assume that K is algebraically closed and finite. So since it's finite, we have elements, n elements, and n elements means that we can have exactly n irreducible monic polynomial, so means that the degree 1 polynomial. So namely x minus c1 blah 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 x minus cn. So we consider the polynomial that is a product of all monic polynomial plus 1. So for any c in the field, the polynomial fc is equal to 1, it's not equal to 0. So this one means that this fx is a non-constant polynomial with no roots. So the previous lemma, yeah, because we say that the algebraic closed field implies that every polynomial must have a root. Okay, so next one, this one is a big theorem. It's the fundamental theorem of algebra. So the complex number is algebraically closed. So this one, instead of proving, I will just use it because there are a lot of proof. There will be a proof in terms of complex analysis, a proof in terms of a topology, and actually in terms of algebra, what I found is we need Galois theory. So I'll skip it first. I just know that I just have a very, very quick research about the proof, this proof. And then I see that then it's characteristic. So here we come to again, I think a very baby version. So this one, every polynomial of degree is irreducible. Is reducible. So the proof is just that we consider any non-constant polynomial in the polynomial ring of the real constant, real coefficient. So by theorem 2.9, we have a complex. We say that it has a complex root z first. So this complex root may be, I think the imaginary part can be 0. So actually here they consider the conjugation. So they consider, okay, so actually is here the z bar is conjugacy. If z another root is the same, the conjugacy is the same, z is equal to z bar, so means that z is real. So means that z is a root. If there's not equal, there's not equal to z bar. So actually, since you are talking about the polynomial degree bigger or equal to 3, x minus z bar, this one is degree 2, it's a factor. I think that one, just doing calculation and say that the degree 2 with coefficient all real coefficient. So we can factorize out something like that. So instead that we can for the polynomial bigger or of degree bigger or equal to 3, we can either factorize out the 1 degree polynomial or 2 degree polynomial and saying that that one is reducible. Here. So calculation z plus z bar and z bar is real numbers.
What you said, if it contains z as a root, then z bar also is a root.
然后这个
啊，什么？
yeah, for here,
Yeah,
for here.
yeah.
Theory Z bar is also root of F. Because when we take conjugacy, it means that the operation means that we can take the whole conjugacy. It's the same if we take whole conjugacy, but after we take whole conjugacy is also equal to 0, means that Z bar is also a root of F. Okay.
So you only consider AI in real. A solution can be in Z bar, can be in complex. Why your coefficient in front?
Sorry?
Can you go up a bit? It's a statement. Oh, okay. Okay. I think it's a bit like the x squared plus 1. So if I can solve it myself, solve it.
Yes. So, okay, this one is also, we're talking about odd degree. Every polynomial of odd degree has a real root. So this one is actually also, I think, similar to the previous part. If we have z equal to z bar, so this one is real, the real roots that. So if z is not equal to z bar, so we can factorize a polynomial of degree 2. So by doing some induction, we can factorize out degree 2, factorize out degree 2 until let the product the polynomial degree 1. So that one is a root. Yeah. So I go to the next proposition. So let F be the primitive polynomial. So this one primitive means that the GCD coefficient is 1. So let P be the prime integer. So assume F mod P has the same degree as F and irreducible in the ZP, the ring of ZP. So then F is irreducible in ZX. So we prove by contrapositive. So if F is primitive and reducible in Zx and the degree F is equal to n. So since we have say that F is reducible, so we can write it like F equal to G hash, where the degree G is the D and degree hash is the E. So degree G plus degree hash is equal to the degree of F. So and then we have DE to be positive, right? So reducing modulo P, which will give the F bar equal to G bar hash. So since we have the hypothesis say that the F mod P have the same degree as F, so degree F bar is same as degree F. So we must have the degree G bar is equal to D and degree H bar to equal to E, because also D plus E must equal to the degree of F bar. So this means that bar is reducible in ZP. Okay. So in other way, if F bar is irreducible, then F is irreducible. So next one, for this corollary, there are irreducible polynomial in Zx and Qx of arbitrarily large degree. So for any degree, we have irreducible polynomial. So this one, proposition 1.2 is yeah. Okay. We have said that f to be irreducible in Rx, and then f is also reducible in the field of fashion Kx. So for Zx and Qx, Q is field of fashion of Z. So if f in Zx is irreducible, that means the f in Qx is also irreducible. By the proposition 1.2. So we only need to consider that the ring of the integer coefficient, the polynomial ring of integer coefficient. So again, by the proposition, we use the proposition list for the mod P. So this one, we need to verify that there are irreducible polynomial in Zp of arbitrary large degree, and for any prime number P. So this one actually also need to use the last story. So I didn't prove that. Okay, so for next essential criterion, so let R be the commutative ring and the P is a prime ideal. So we have any polynomial in the polynomial ring of coefficient R. So we assume that an, the coefficient of xn, is not inside the prime ideal, and a for a0, a1 until an minus 1, it is in the prime ideal, but for the first term, a0 is not in the prime ideal square, p square. So then f is not the product of polynomial degree smaller than n in the Rx. So again, we prove by contradiction. Not product polynomial degree smaller than n means that it is irreducible. So assume f equal to gx. Again, so we have like degree of g is d, degree of h is e. So this one we already go through the proof before. So we write down g got degree d, something like that. We write down like this, and h a polynomial degree. So again, consider f modular p. So we have f bar equal to g bar h bar. So therefore, f bar denotes f bar denotes f modular p. So by our hypothesis here, so this one is hypothesis, and then this one is contradiction. Because they need to satisfy three things, right? This proof is just consider not satisfy one of the things with other two things is satisfied. If one, because we prove by contradiction, right?
Contradiction is assume that f is a product of polynomial and then contradict one of the hypotheses.
Yeah.
You also assume that first, but then you get contradiction.
Yeah, but from here we use the first 2 points. We didn't use the third point.
No, I mean you must use the third point so that you can get contradiction.
Yeah. Okay. Sorry. So we say that for any a0 to n plus 1, the ai is inside the p. So after modular p, it disappears. It remains an bar. So the term a0 until an minus 1 finish. So we since the our portion P is an integral domain, the factors of f bar must be also monomials. So the g bar must be also the last term, b d bar xd, and the hash bar is also the c bar xe. So and we have that since the degree is equal to 0, this implies that the b0 must be in P and c0 must be in P. Because the b0 is c0 is vanished. So then we have the a0 is equal to b0 c0. This is in the p squared contradiction of the statement that a0 is not in the p squared. Okay. So example, the first one for all and for all price p, the polynomial x to power n minus p is irreducible in zx. So we look at the 3 points, a n is equal to 1, it's not in the p. So a0 is equal to p, so it's not in p squared. So again, for the first term until 0, 0, 0, 0, 0, until the n minus 1 terms also 0 is in p. So we said that x to the power n minus p is irreducible.
What's 0, 0?
The coefficient of x, coefficient of x squared, coefficient of x cubed, until the coefficient of x to the power of n minus 1. And then the second one is a little bit hard to see. So this one is actually called a cytotomic polynomials, and they are irreducible. So that one is a little bit tricky. So actually, if we directly look at it, n is equal to 1 is not in P, and a0 is also equal to 1 is not in P squared. But the a0, a1, all is 1, 1, 1, 1, 1, 1, 1. It's not in P. So actually, if we want to have, if we want to let this tree become true, we need to do some change of variable s equal to y plus 1. And then this one is actually the geometry series equal to xp minus 1 x minus 1 over x minus 1. So after the change of variable, we have 1 y minus 1 to the power p minus 1 over 1. And then we can have yp minus 1 plus pc1 yp blah 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 p minus y plus p minus 1. Okay, from here actually we can have the three properties. Okay. Yeah.
How do you get the P? The P is the concept of what? The prime ideal. It's the power or is the
maybe I'm not sure how to write.
No, what prime ideal you are choosing? What's the prime ideal you need to choose?
I think it's
For
the
Einstein condition.
I think it's the idea of the prime integer that we choose.
I mean, like, so the second prime happened in the power, and then the first prime happened in the constant. So constant matter or the power of the highest power matter?
Atom means
Matters.
or matters.
Yeah.
Oh.
What's the Einstein condition? What's the prime ideal talking about?
We need the prime ideal and the
Yeah. So it is the let R be a ring that P we assume that this prime ideal is random. Fix the P.
I think fixed. We need to fix the P such that
You just need to find a P that works. Very fancy. Any P that works, that it works.
I think it's
But then I mean, I think you can find the P from part 2. You need to make sure that AI is in full. So in this case here, if you pick P equals to 1, then will be 3. Okay. So
one is
one, one is not prime.
Yeah.
Okay. Maybe you can continue.
OK，
啊，好了没？
没有没有没有没有
喂，你找什么 P？解决了没 P？
啊
？P 耶？新的 P 要怎样
不知道，我怎么知道？
？What？我不知道怎样 show irreducible。结合 P 是什么？你不是跟我们讲要换 change variable 然后
But I'm not sure 嘞，为啥？
什么叫 not sure？不然你再 change 来做什么？你就找一个 P such that 这个 coefficient 是就符合你那3个条件。
让我想一下。
就有没有直接写在你的那边？
因为我没有想要找 P，
哎，你编这个给我们看中了，
那么继续做。
离谱。你可以给一个 P 然后叫我们继续 verify。I think 就是咦，这全部 factor contains with P 哈。
Yeah, I think it's P is
P 吧。把 A0是0啊，这个哦没有的 ，A0是 P over P 减1，肯定就是 P 吧，是吧？现在全部号码都是 P 倍的，然后第多少 P？ P choose 的 formula 是什么啊？P factorial 除 P minus P P 的 factorial 什么？那个 formula 写出来。 ，so 你会 remove 掉谁了？p minus 1 factorial 会 remove 掉谁？这个东西讲看了2块。and then p minus 1 factorial 这样出来。那 n factorial 我可以 cancel 掉嘛，对不对？
对。
p minus 1 factorial。
有两个 p 确实 p 然后 p minus 1没有看，p 没有
p minus 1不用看，
前面这是高 p
对，
然后你是大 p 确实 p minus 1里面，到 p minus 1全部都会掉，剩 p 了。
哦，你讲最后一个啊，还没来中间那些
那些就
啊
，P 啊，
我的妈 ，p 这么 p 会在我的手，这么你可以 prove 它是有 p 在里面，还没来 multiple p。
就是其他就是它 p 乘 p 减1，然后就 p 乘 p 减1 p 减2，就 p 乘 p。
对啊，
就是有
不是它有除东西吗？
就比如讲你 p 的7是没有，如果你是 7选3个啊，就是7里面5，然后3个1了。然后如果你 p 是因为 p 是 prime 嘛，这样的话你就什么都好的会有一个 p 在那个第二个。
对，我的意思是说，我讲看这个东西，我讲知道。Yeah，
就是这样，可以 factor 那个 p 出来。
对，这样做。
那不可能有 p 的，就
都可以给它 P 出来，P 那个。
But then like 剩下的东西全部是活在这里面，剩下的东西怎么活在这里面？
就剩下的东西活在这里面。
要吗？不是，你要 multiple p 了。I mean n factorial 我可以割掉 ，but then p minus 1 p minus n factorial 我这样 make sure 我可以割掉。
这里就是有多个连续的号码，你就可以除多少个。这样比如讲你4个连续的号码，它一定可以除4个不同的。
不懂什么来着？
比如随便拿一个5、6、7、8，或者是11、12、13、14，它一定可以是除4个不同的。如果你拿4个，
为什么？
为什么？因为如果你4个连续的，一定会有一个是4个那个
multiple，
and
then
4、一定会有8个 multiple 噻。
8个 multiple
有8个 multiple，然后你就 check 是不是有3个 multiple 就可以了。
OK，把人家呢这样子啊？
如果懂完那个就可以用了。
为什么？
因为你这个 choose 是这样的，比如讲你7、2我放弃，7选1、7选2，都是 来，你7选2就76，那你除2的 factorial 嘛？
7 factorial 除5 factorial 的，除2 factorial。
就你那个 p 减 n 的 factorial 代表说它有多少个号码在上面，
嗯哼，
所以如果有5个号码在上面，你除5的 factorial，这样你可以除到
有没？不知道没？
3个。
啊，
剩下那一堆，
啊，
剩下那一堆很不一定是 integer 啦，
不一定，不一定，
呀，
对，不可能呢，那你不可能，那不可能，你这个东西选出来了，
哦，一定
一定是题啊，肯定，只是说来怎样 cancel 吧。还有多少东西啊？
很多，
啊，还有很多吗？
我有一个 session，
哦，还
你
有一个钟，
可以给我讲，
还有一个钟啊，
还有一个 session，
还有一个钟，
你给我讲啊，
我们可以 break 一下
breaking。
好的，
你这个你解一下，
好的，
感觉有一个 treatment for m 会啊，要 prove 这个东西，
上锁。
厉害。
嗯，诶，这样写一下感觉变比较容易些。诶，如果 P 变 P 加 N 好像变比较容易。P 变成 P 加，
皮夹，哦，
就是来我 change variable 现在它都出讲这样 make sense。
皮夹，
嗯，对吗？
变成皮夹，
啊，三个东西，不太对，不太对。你你，要传一个东西，有传一个。这个第一个跟这个 P 减 N 加一，看这个，P 减 N 对吧？
嗯，
啊，对啊，and then 继续，对啊，不对啊？
一个 n 加一，然后就 n 加一个 n，
对吧？如果把 n factorial 的东西全部切掉， 哎，不对，
你这应该是剩下 n factorial。
应该是 n 加一，然后 n 加二这样啊，拿到 p 啊，
啊，
或者啊，
你那个
这样也有几关哦，
你那个上面那个 p 减 n factorial 换成 n factorial 不会。
啊，这个
嗯，不是我自己讲，这个
嗯。
你现在上面做的东西是把 p 减 n factorial 去掉，
哦，我是把 p 减 n 去掉，
嗯，
所以我还有
你剩下
n
n
factorial。
factorial，
哦，OK
要
OK
删
OK，
掉吗？删
反度啊，
这个，这样子可以啊，然后也删在这边，
嗯，这样，
嗯
n factorial，
对，
然后怎样 make sure that n factorial 除了掉呢？你刚才讲这边剩 n 个东西，
是，然后现在是那种样可以不确定它出道
啊，应该是这一部分可以除到的，
啊，
这样，
sorry，
那加一 n，那加二一个影响，
减一，
那 n 那加一 n，那加二，
减一啊，减二，
对啊，那个 p 啊，
啊哈，
我 p 我 set 它是想想给你玩。就如果我们要 test 一个东西能不能出，它是不是3.2，是 test 它是不是3k 加一，三
对
k
对
加二的感觉。
对，
是啊，
是什么？
嗯，来那个 P 啊，
嗯
还有我们把所有可能性想完了，想来 P 一下n 的 factorial 乘 k
嗯，
maybe 啊，n 的 factorial 乘 k，如果 P 等于是 n 的 factorial 乘 k，这样它第一个就可以跟 n 的 factorial 对调。
嗯
如果 P 不是 n 的 factorial 乘 k，这样是 n 的 factorial 乘 k 加一，is two 啊。if P 是 n 的 factorial 乘 k 加一，这样你的 P 减一，它就是 n 的 factorial 可以除。
这个 p 是 prime，
所以就 n 的 factorial 乘 k 加一哦。
嗯，n 的 factorial，
慢慢试啊，一个是加一，然后你带进去看它有没有可以除 n 的 factorial。就它如果它加一这个，它加一，你带进去 P 等于 n 的 factorial 加 n 的 factorial 乘 k 加一，你带进去这边啊，它就可以这边除了 n 掉了。
n factorial 也太大了吧，我 p 怎么可能是 n 哦，对，可能加一了。
一个4啊，然后加2，然后4加3，
But then 我的 p 不一定是什么的 factorial 加一吧？
就试完全部号码就对了，试完全部可能性。
就它可能不是加一，不是加二，但是可能加某个东西这样啊。啊，
But then like 它不应该只是对着一个除哦，现实生活中它是对着不同的地方除掉，
对啊，对不同的地方。
肯定啊。你拿几个号码来 try？
嗯，
来，你拿一些号码来 try 啊。
哦，你是讲它可能这边各条
对呀、这边各一点，那边各一点啊。啊，但是你比例它是 integer，不代表它是 multiple of p 啊。哦，它是不是 integer 这个我也不能讲出来。对呀、integer，但是重点是我们要它是 multiple of p 啊，对不对？我们要说啊，在那个 prime ideal 里面，你 integer 也不够。反正它为什么是 integer 我也不知道。I mean like 它好像是有一个 trigger，现在我忘记了。
是不是 n 的变量是不是用 n
啊？
来 p 慢慢带进去哦，n plus one n plus two 一个一个四
啊
，n 接 plus one n plus one 套上，对吗？然后它就可以不一定要一整个个完了，
对对
它就可以
对
各项可效
对
就可以了。
对对。But then like 它应该是有一个 general argument。因为我没有做过咩？我记得我是做过。我说上次在讲一个东西的时候用的。但上次讲那个什么 group 的东西的时候用到的 silo 的东西，silo 的时候我不是有用到这样的东西，讲 silo。希望是希望变
出现一个几个意思。
哦。哦，不太一样，不太一样。
但如果我们相信
但是呢，
this one is integer，没有这个是 integer，这个是 integer，这个 suppose 应该是 integer。
哦，你是这个意思。
然后 p 出现是 integer 那个东西，
不是你还不知道为什么 p 一定 divide p over n，现在这个是这个问题。你这个 let 是你已经 assume 那个 p choose n divisible by p 啊，我们现在就是要 prove 这个东西。
我可以选我 p factorial，我可以选 p 出来啊，它肯定是 divisible，那不是？
没有啊，divisible 的意思是你要乘一个 integer，你不是把 p 拉出来吗？比如说我们不会说三可以除2/3，我们没有这样讲啊，我们没有讲三可以除2/3，2/3，哎没有2/3，2/3不能被删除哎。除的意思是来你要乘一个 multiple of that，你不是拉出来吗？
OK，听他说，
2/3可以被删除。
解锁，请取出话筒。
但是可以除哦。
可以除的是你整除，
啊，对对对对对，可以除了一人分0.5个。不可以整除呀，不可以整除。怎么你不然就会讲这个？
嗯，
他书里面讲 change of variable，
没有，
人怎么忽然间 change of variable？
我问 AI 啊，
然后 AI 没有跟你讲那个 prime 是什么？
我 assume 它就是 P 了啊，我觉得 P 应该错掉了。
啊，然后你没有去 verify 啊
对啊，我觉得 set this out right because that one is not going to the right.
？What do you mean？什么意思？
啊，那你就属于
不然我讲 verify 呢
你，哎呀，就这样。
算一下，问的是对的。
Okay. Okay, so next part, we will have three examples, but I think two examples only, but one of the example they separate the two parts. The first part is Chinese remainder theorem. So that one, I think last time I have asked Yuhan, and then Yuhan said that we didn't learn Chinese remainder theorem, right? So this one, okay, very quick recap. So, we let it be the integer case. So if we have any pairwise corporate integer and one, and can means that the GCD for every pairs of integer is equal to one. Would be okay. So and we have a system is the S is congruent into A1 mod and one and until the X is congruent to AK mod and K. So we want to find X in the terms of A congruent B. So we want to find the solution like this. And then this theorem says it has a unique solution of modular n big N. This one is equal to the multiple of the complex integer. And then for this one, actually also we can find it, but here we no need to find. We just need to know that there's a unique solution of modular. And so equivalently, so this one is very related to what I want to say in the next. So the map from the Z to Zn1 times blah, 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 times Z and K is surjective, and the kernel is nz, big nz. So we have this isomorphic by the first isomorphism theorem. Okay. So we have a theorem like this. This is very similar. So let ideal I1 until Ik be the ideals of the ring such that Ai plus Aj is equal to 1. So do you know what is Ai plus Aj equal to 1? So here is combined integer, right? And then this Ai plus Aj equal to 1, it means that there is this R in Ri and S in Ij such that R plus S is equal to 1. So actually call maximum. And then we have the natural homomorphism like this one is correspond to this one. So from R to the R quotient I1 times R quotient I2 and then to R quotient IK. So it's surjective and then so we can have the isomorphism R quotient I1 times IK is isomorphic to this one. So actually for here It's okay. We want to prove this, but we need the two lemma below. The first lemma, again, I want to IK be the ideals and then the co-maxima, and then their product is equal to their intersection. So we consider the proof, we consider the induction for case k equal to 2 first. So I and j be the ideal. So such that I plus j is equal to 1. So actually, ij is in the I intersect j is holds for all ideals. This is obvious. So we need to prove that I intersect j is in ij when I plus j is equal to 1. So when I plus j is equal to 1, so yeah, this is the definition. There's element A in I, B in J such that F plus B equal to 1. So, but when we have an out is in I intersect J, so out is equal to out times 1 is equal to out, because we say that F plus B is equal to 1, substitute F plus in inside, and then it's equal to out F plus out B is in IJ. So, because RA is in IJ, RB is in IJ. So this one, okay, we already proved that. So actually this one, the kernel is equal to the I1 intercept IJ. And then you show that by lemma we show that this one is equal to their product. So again, the second lemma. So their co-maxima I plus AK is equal to 1, and then so this one actually a little bit like doing induction. So we have I1, the product of I1 until k minus 1 plus IK is equal to 1. So hypothesis for I equal to 1 until k minus 1, there exists a such that 1 minus AI is in II. So we have their product is 1 minus A1, 1 minus A2, and then until 1 minus AK minus 1 is inside the product of A1 until AK minus 1. So if we have the 1 minus that kind of thing, there will be IK. So because that one is a combination of A1 until AK minus 1 in the IK. So yeah, we have done proving it. So next one, we prove that the theorem 3.1. So I screenshot here. Okay. So firstly, the natural homomorphism the canonical projection from R to the R quotient I. So and the universal property of a product. So actually here I want to say that the kernel is actually equal to the intersection of the ideal. So by lemma 3.2, we say that the intersection is equal to the product in the first isomorphism theorem. So the second part of the statement, which is the isomorphism part, is automatically true. So we only need to prove the first part, the surjetic part. So we argue by induction. So we argue by induction, and actually we need to use this lemma a little bit more like induction lemma. Okay, so for k equal to 1, there's nothing to show. So for k to be bigger than 1, we assume that the statement is known for fewer ideals. So we assume that the natural projection induces an isomorphism. So until the k minus 1 terms first. So we want to prove this one is surjective. So actually, by lemma 3 by 3, we have this one is comaximum. So we go to reduce the case for two ideals. Two ideals is like this. So two ideals will be like the I and J. So again, here we have ij is co-maximal, and then let any Ri and Rj in R. So we have to verify that there's a R such that R is congruent to Ri mod I and R is congruent to Ri mod J. So here is a little bit like a Chinese geometrical theorem. So since I plus J is equal to 1, so again the definition A plus B, A in I, B in J such that A plus B equal to 1. So we let R equal to A Rj plus B Ri. So this one is actually also a technique of Chinese geometrical theorem. So R equal to R A Rj plus 1 minus A Ri is equal to Ri plus A Rj minus Ri. So it's congruent to Ri mod I. So for another part, R is we let A to be have equal to 1 minus B. So after that we have the Rj mod J. Okay, so we've done proof.
This is the surjective part.
Yeah.
And then this is the base case.
Yeah. See. Okay, so this one is sorry. This currently okay, I didn't prove that, but it's an immediate consequences of theorem 3.1. So I just let out your PID. So for any GCD, for any element in R, so that the GCD is equal to 1. So let A be AI A1 until AK, the product of AI until AK. So the function is like this, defined by R plus A goes to the R plus A1 until R plus AK is isomorphism. So this one is a direct immediate consequences of the theorem above. Just this one is a smaller case. Okay. Next one. Next example is Gaussian integer. So this one I think is not is familiar to you. So the Gaussian integer we define as zi, which is the x quotient x squared minus 1. So it's actually any a plus bi such that a and b is in the integer. A and b is an integer. So for have better understanding, I introduce an integer like this here. So the x-axis is the real part and y-axis is the imaginary part. So here we have the ideal. We can plot something. There's a regulation for some ideal in Zi. So this one is the right side is the ideal of -2 minus I. So it's actually minus I A plus bi such that A B in Z. Also there is a name for this. This one is called superimposed lattice. Later I will use as a proof, but you can consider a superimposed lattice just as an idea of something, the shape of the idea of something. Okay, so the norm function just we let any a plus bi after under this function to be s squared plus b squared is like a distance squared, something like that. So here the function is a Euclidean valuation of zi. So n is a multiplicative in the sense, so z nzw is equal to nzw. So here the multiplicativity is immediate consequence of the elementary properties. So we have the conjugate, complex conjugate, and then we can quickly prove that nzw is equal to nzw. So we need to see that what we left is we need to show that n is Euclidean valuation. Okay. I recap what is Euclidean valuation, right? Okay, Euclidean valuation is for all z in zi, for all w not equal to 0 in zi, and then for all qr in zi such that z is equal to qw plus r with r equal to 0 for nr smaller than nw. Okay. So here we let zw is in the zi and w is not equal to 0. So the ideal w, okay, is a lattice superimposed in I, so that we can plot something that have the regulation on this integer lattice. So again, division z over w can be performed in zi. So the given z, we have two cases. It's either in the vertex or it's not in the vertex. If it's on the vertex, so we can have the r is equal to 0. And if not, we can have the distance between the closest lattice QW. So we have Z equal to QW plus R, and then R equal to Z minus QW. So it looks like this. So here, now we need to show that NR is smaller than NW. So NR is actually, we say that R is equal to Z minus QW. So it's actually the distance here. And NW is actually the distance between the, along the vertex. So from here, visualization, we can easily know that NR is smaller than NW. Okay. So the next one, the units of Zi is plus minus 1 and plus minus I. So this one is, if U is a unit, so we have exists of V such that UV is equal to 1, then NU NV is equal to NUV is equal to 1, and yeah, N1 is equal to 1. So by the previous proposition for the multiplicativity, so we say that NU is also a unit in Z. So this implies that NU is equal to 1, and only one, the only elements in the Zi is with norm 1 is plus minus 1 and plus minus I. Okay, so again here, let Q be a prime element, so there is a prime integer P such that the norm of Q is equal to P or P squared. So here we say that Q is a prime integer, so prime is not unique. So this means that NQ is not equal to 1 by the previous lemma. So NQ is non-trivial product of integer primes. So since Q is prime in the Zi, Q must derive one of the prime integer factors of NQ. So we let P be this integer prime. So but then we have the Q divides P in the Zi, and it follows also by the multiplicative of the norm that the NQ is divided by NP, which is the P squared. Okay, NP, because P is a prime integer in Z, so NP is P squared. So we say that since NQ is not equal to 1, the only possibility are NQ is equal to P or P squared. Okay. The next one go to the Fermat theorem of sum of square.
IQ is 2 must be 5.1. IQ must divide 1 of the prime factors. Q 一定要 divide 1 of the factors. Q 一定要 divide. YQ must divide 1 of the prime factors. So NQ 的 prime factor 一样。
One integer factors.
Since Q is prime.
There's something like this, right?
NQ is fixed, right? NQ is defined as Q times conjugate.
Yeah.
Mm.
This is the expert has this set.
Okay.
So
So
so we must have Q divided NQ in the diagram.
yeah, so no, you see, so what's the divisibility? Yeah, so when you talk about divisibility, right? So what do you mean? NQ is in Z. So Y.
Q is in diagram.
So Y Q must divide. Says that Q is prime. What's prime again? I think this is not the prime number prime.
If Q divides the product two elements, then I divide X or divide Y. Divide one of the elements.
But then why Q have to divide one of them? So it says that Q is prime in Zi, but Z is in Zi. So Q must divide one of the prime integer factor. But Q is an element in Zi. What's divisibility here mean? I mean, like NQ is Z, right? How is an element in Zi divide things in Z? Is it possible? What's divisibility here? How do you divide here? What's the definition of divide? I only know how to divide in Z. How do you take Zi element to divide things in Z? Simple.
I think it's like doing some the okay, say is it possible?
How do you divide how do you define divide in using element in Z?
Rationalize the denominator when we divide.
How do you, for example, I can divide what? I divide 2I.
Divide one.
I divide 1. What do you divide? They don't define divisibility in ZI. Your saying teacher. Did they define? Did they define divisibility here? They should have.
divide I divide I square，
I divide
然后我们可以写成 I 等于 I，然后读成 I 做上去，这个算 divide 是可以的。I divide I divide I square equal to I 可以写成 I，然后读成 I 做上去，因为 I 包5的话还是因为 I 而已。
对，
所以这个就是definition of divisibility 在
make sense 吗？这个 definition
在这两者在 I 真的。
是吗？是这样。
我想的是这样子啊，divide。
前面他们 define divisibility 的时候，就是用这个 a divide b then a equal to c。
Very.
Let's see there is a b h。
I mean is Q1 plus Q2 I. Then I will get Q1 minus Q2 I.
Then Q must divide one of the prime integer factors. 什么意思？
It means that
So 你要把这个 Q bar 想成 product of prime.
yeah. And Q is a product of prime numbers.
Q is a product of prime numbers.
We can do like this, right? Because any integer we can divide by the prime number, they are a
Product of prime.
product of prime.
But then
They say that it must divide one of the prime integer factors, one of the prime numbers. So we let it be P.
Okay, I think 如果那样的话就 make sense，因为 Q 要 divide Q times Q bar，but then 你可以 write Q by Q bar as a product of prime integers。And then prime integers 也是跟 prime in Z 也 ZI。
Yeah.
So Q
这样是
啊，
这样是
that's yeah. So I mean like Z, if Z is a UFD, then ZI should be a UFD, right?
这样算
And then 因为我们 prove 的是 polynomial ring 是 UFD 不是？ But then 这是 quotient of polynomial, quotient of UFD 啊。quotient of UFD 还是 UFD？ quotient of UFD 还是个 UFD？
What do you mean quotient of UFD?
Like ZI is a quotient of UFD。 我们是 prove R is UFD, then RX is a UFD， But then RX over I 也是一个 UFD 的，所以真过。quotient of UFD 是个 UFD 的。quotient of UFD 还是 UFD？ 没有真过。But then 有这个 statement。
有讲就是三个平
啊？
有讲就是三个平。
UFD 哪来做？
有讲就是三个平啊？只能就是三个。
你讲完有用没？有用没？你讲完一下。
没用吗？
我不知道，你觉得有用没？
怎么没用？
我不知道，我就问你。
我讲这个三个东西不有用。
就算给你讲完它有用没？
怎么没有用？
我不知道，可能没有用。
用 for what？
Yeah，所以啦，我就想用来干嘛？讲完之后啊，讲完意义在哪里？
你讲
所以咯，讲啊，你要讲完它。
哦，
他讲什么？然后3.5
对
是有人超过
有。
对啊，
这样的。
嗯，
Okay, the last paper, the first one, I just quickly go through. So the pi p split the I evaluate is the sum of the two squares. So actually, we can split the integer. This evaluate graph. So this one is this one is if it's the sum s squared plus b squared, then we can split uh into a plus bi and a minus bi, and then we use the norm, and then we found that so either the two factors is unique or is in a unique, so p is not reducible, so it's not prime. In the end. So conversely, we assume that p is not irreducible. So it's a irreducible factor. So we use the previous thing there. So the x is either p or p squared, but it's not equal to p squared because there's not associated. So we have p to equal to we are forcing p equal to s squared plus b squared. So this one is a bigger, it's a longer proof. So this one is actually a little bit of the we play with number theory, something like that. So positive or prime integer splits in that if and only is congruent to one modulo 4. So the previous we only have the integer prime, and then this one we add one more condition, the prime is odd. So actually we have the isomorphism here.
我觉得我们要停。OK，所以我讲为什么讲完没有用，是人家听不懂你讲完也是没有用呀，这是我要讲的点。就是说，你讲完或没有讲完没有关系，重点是你要讲的东西能讲明白，因为如果人家不明白，你讲到完也是没有用，这是我意思呀，就这样。